Right, Assalamualaikum warahmatullahi wabarakatuh. Welcome to the second video for your physics online learning. This is the second week of your online learning. Now, for this week, we will cover two topics. The topic about radioactivity and introduction to radioactivity. That's the first topic that we will cover this week. And then we will cover the second part, which is the characteristics for the three different types of radioactive emissions. So we're gonna go a bit faster this week by covering two topics. Um, these are the learning objectives for this lesson, and these are the things that we will go through for this lesson. So let me just briefly talk about what we will go through for this lesson. Firstly, we will look at what we mean by radioactive decay. And then secondly, we will look at how do we detect the radiation, so methods of detection. And then thirdly, we're going to look at the randomness of radioactivity. Uh, what sort of characteristic does radiation have in terms of its randomness? And then we will look at something that is called the background radiation. And then after that, we will look at the three different types of the radioactive emission. So their nature, their ionizing effects, and their penetrating powers, and also how these three different types of radioactivity deflect inside electric fields and magnetic fields. So these are the things that we will go through today. And these are the things that you are expected to know by the end of this lesson and for your exam. Right, let's start. Radioactivity comes from the atom, especially some isotopes. Some isotopes have an unstable nucleus. So if you don't know what I mean by nucleus, you know what atoms are. So atoms, in the middle of the atom, you can find the nucleus, and inside the nucleus, that's where the proton and neutron belong to. So in the nucleus, in the middle of the atom. Some isotopes have unstable nucleus because that's their nature. And because they are unstable, they will break apart. So what we mean by break apart is that because they are unstable, they will break apart. They will split into two new atoms or two new nuclei. Right? So these nucleus are unstable. This nucleus is unstable, and then it will break apart and then split into two nuclei. And when it breaks apart, it will emit radiation and a particle. And this process is what we call radioactive decay. Why is it called decay? So decay is just another word for something that is breaking apart. We often encounter this word whenever we talk about death. Uh, we say when someone has died and has been buried, over time the body will decay. So that means the body will break apart, the flesh will deteriorate, and then what's left of the body is the skeleton. Same thing here. So radioactive decay involves the breaking apart of the nucleus of an unstable atom. So the formal definition of radioactive decay is in this box here, so I'll read it out for you. Radioactive decay is the process by which the nucleus of an unstable atom splits up by emitting radiation. So it's unstable, it breaks apart, splits up to two new atoms, and it will emit radiation. During the process of radioactive decay, so when an atom breaks apart, um, it occurs at a spontaneous it occurs spontaneously. So what do we mean by spontaneous? You probably have heard of the word before, spontaneous. That means it occurs at random. You cannot predict when it happens. It's random. And the radiation that is emitted is in a random direction. That means you cannot predict whether it will shoot the radiation out forwards or backwards, up or down, east or west. You cannot predict in which direction the radiation will go. So not only it decays at a random rate, at a random occurrence, it will also give out the radiation in a random direction. So everything is random. You cannot predict where and when the radiation will happen. Isotopes that give off radioactivity are said to be radioactive, and they also have special names for these radioactive isotopes. They are called radioisotopes. So here I have an animation of an unstable nucleus. So in this case, we have polonium-211, and you cannot predict when it will decay. So let me just play this animation and you will see what sort of thing will happen. So it will decay eventually, it will give out radiation. I just do not know when. Okay, so there. Did you see that? And then when it decayed, it became a new atom. So from polonium, it became a new atom. In this case, it became lead 207. So let's just play that again. So that probably took like 5 seconds to decay. Now with the I played it. There you go. Okay. So it occurs randomly and you cannot predict when it happens, and you cannot predict in which direction it will give out the radiation. Here's a different example. This time I have, let me just pause it. This time I have several polonium isotopes here, and you will see, even though they are the same, they are the same isotope, they decay randomly at that random times, and the radiation that they will give out will be given out in a random direction. So I'll play it here. Okay, just waiting for this one to decay. There we go. Now all of them have decayed. Let's add a couple more and see what happens. Okay, there we go. Radioactivity is invisible. It has no smell. It has no sound. You, uh, using our normal human senses, we cannot detect radioactivity. Now, some radioactive substances, they can be quite harmful. It can be damaging to our body, and it's even more harmful knowing that we cannot detect them. We do not know we do not know it's there. So in order to protect ourselves against harmful radiation, we need to figure out a way or use a device in order to detect this radiation. So what is that device called? That device is called the Geiger-Müller tube and counter. So as you can see in this picture here, there are basically two components to this device that measures radioactivity. First is the Geiger-Müller tube. So that's the tube that will detect the radioactivity. The short form name of this tube is called the GM tube. And then the tube is connected to a counter, or also can be called the rate meter. So what the counter does, the counter, like its name, it only counts the radiation, like 1 radiation, 2 radiation, 3 radiation, so on. Right, so you have the Geiger-Müller tube and it's usually connected to the counter. When radioactive particles enter the GM tube, it will make a clicking sound. So after this slide, I will put a video that shows what this sounds like and how the GM tube looks like and how it is used. The counter for the GM tube counts the number of detected particles per minute, or otherwise known as counts per minute or count rate. So the unit for radioactivity is counts. So that means how many counts, 1 count, 2 count, or 3 count. Or it can also be counts per second. So in 1 second, how many counts have been detected by the GM tube? It can also be counts per minute or counts per hour. And it can also be called count rate. So in a certain count rate, the word rate is basically related to time. So how many in a certain time the count has been detected. And another unit for radioactivity is also activity, right? So how many activity that is detected. So 100 activity, 200 activity, and so on. So these are the units for radioactivity.
Now you're being silly, aren't you? I'm going to send you all off, and you're going to find a place to hang your balloon, and then when you get there, you're going to charge the balloon by rubbing it with the cloth, and we'll go back and collect it. Release the air out slowly as you let it down onto the paper. Here I've got a balloon that has not been inflated and has not been around the lab. I'm going to test it with the Geiger counter to see if I can get a count from it. As you can see, there is no count. Jill, would you like to pass yours across? And if we test it with the Geiger counter, we can notice that there's a significantly higher count.
That's quite a difference.
It is, and that's not really what you would expect from just hanging it in the corner of the lab.
So it's become radioactive over an hour then?
Oh, let's be careful. Has the balloon become radioactive?
It's just attracted the dust particles.
Good. Something stuck to it.
Yeah, so by charging it, what we've done is we've had the dust particles stick to it, and those have got the decay products of the radon gas that is found naturally in the air.
I think the balloon experiment really stands out because it's interactive.
Some everyday objects will register on a Geiger counter. The results may surprise the students. First is a domestic smoke detector.
And there's a slight count, and the reason for that is that inside the smoke detector is an americium source, which produces alpha and a small amount of gamma. The alphas are stopped by the smoke if it's inside the chamber, which will then trigger the alarm to sound. So yes, it's radioactive, but not very.
That's quite surprising because you wouldn't expect a household product to be made with a radioactive source in it.
You could also try an old watch with a luminous dial.
Wow.
Whoa.
So a very significant count there.
Yeah, the worrying thing is I'm sure I had one of those when I was a kid.
Right, so in the video, you probably have noticed that even though the GM tube is not near any radioactive sources, it still measures a count of radioactivity. What is that? Why does that happen? That's because of something called background radiation. So this is the radiation coming off from the things surrounding us. So a lot of things in this world, they are radioactive. So these are some of the examples here on this pie chart here of some of the radioactive substances that are always around us. So radon and thoron, they are radioactive and they can be found in the air. And background radiation is just harmless radiation. It doesn't do that much damage to our body. Our body is used to it, and there's usually a small amount of it around us. So background radiation can come from radon and thoron. Background radiation can come from rocks. Even the human body gives out some sort of little bit, just a small bit of radiation. And radiation can come from cosmic rays. So that means radiation from the outer space, usually from the sun or any sort of star, can also come to the earth and we are exposed to it. Medical equipment and substances can give out radiation. Fallout, so I don't want to talk about that. And just like medical equipment and substances, industrial equipment and substances can also give a bit of radiation as well. So background radiation, what we mean by background radiation is the radiation that comes up from things that are usually around us. It's very important when you are calculating or measuring radiation from a radioactive source, you need to minus or deduct the radiation that you measured from the background radiation. So what do I mean by that? Say, for example, you have a background radiation of 2 counts per second, right? And then you measured an isotope. So let's say this isotope is X, and it has a radiation of, let's say, 200 counts per second. So that is actually not the actual radiation coming from X. So what you need to do is in order to find the actual radiation, is that you need to minus the radiation that you measured, in this case 200, with the background radiation that is always there, in order to get the true amount of radiation. So in this case, it's 198 counts per second. Okay, like that. So always take into account the background radiation when you are doing any calculation regarding radioactivity. I'll share a link to a video that explains background radiation, and the video also shows you the different locations with different amount of background radiation. So some locations in the world have a lot of background radiation, a lot of strong background radiation, and they can be very dangerous. But mostly, most places in the world, the amount of background radiation is quite safe.